In this video, I'm going to show you some of the ways 0 and 1 play parts in a lot of mathematical understanding. Many times we overlook it or assume that everybody knows the connection or this fact, but highlighting the connections can help students make their own connections, which can produce much deeper understanding and a better memory. We will start with the links connected to 0. Zero does exist. It is a real number, which means it can be plotted on a number line. 0. It is the very center of every number line, which means that it is a rational number. It can be written as a fraction. It is an integer because it doesn't have bits and pieces, and it's also considered a whole number. It is not considered positive because it's nothing. 0 also represents nothing as a quantity. So for instance, if I asked you how many apples are in this box, you can't just not say anything, so you say 0. There are 0 apples in that box. It represents the quantity. 0 also holds space for nothing. So when nothing is there, you want people to know there's nothing there, so you have 0 as a placeholder. Here's how it works. This is the number 1. All I have to do is put a 0 placeholder in the ones place, and now it's not 1 anymore. It's 10, 100, or 1,000, or 1/10, 1/100th, 1/1000th. You get the picture. It holds a space showing that there is nothing there. So even though there is nothing in the ones place in the number 10, if all you had was the number 1, how would you be able to tell it from the number 1? So 0 has a lot of different functions. Link number 2 for Zero My Hero may seem rather really obvious and not necessary, but this idea comes into play in a lot of algebra and understanding techniques for solving equations, and that's the fact that adding 0 has no effect on the original number. Started with 3, added 0, I still have 3. That's one of the basics for solving equations, is to get one side such that you have 0 added. It's called the additive identity. And identity is a particular kind of problem in which whatever you're doing has no effect on the original thing you started with. So I started with 3, I added 0, it doesn't make an effect, so I still have 3. That's what an identity is. There's several of them that involve 0 and 1. Link number 3 for Zero My Hero is making zeros that make solving equations easier. And understanding that 3 minus 3 is 0 and negative 3 plus 3 is 0 is what helps you do this. So we'll take the equation x plus 3 equals 8.75. If I need to figure out what x is, let's say it's something I can't actually do in my head, even though I know the answer is going to be 5.75, I need to get rid of the plus 3. So I know how to get rid of plus 3. I know how to make 0. 3 minus 3 is 0. So I'm going to subtract 3 from that side. I just made 0. But remember, in order to balance an equation, whatever you do to one side, you also have to do to the other side, simplifying both sides. The plus 3 minus 3 is what makes 0. That's what makes this method of solving equations possible, because on this side now, you have x plus 0. And I know that x plus 0 is just x. I just isolated my variable using 0. Link number 4 for Zero My Hero is the multiplicative property of 0. And that one property of multiplying by 0 is that it makes everything 0. Multiplication is about repeated things. So you're adding some number repeated number of times. So 2 times 3 is 2 plus 2 plus 2. 3 2's added together. But it was 2 3 times. If you're going 2 times 0, you don't have any 2's multiplied. You have nothing. You have 0. So 0 groups of anything is 0. And understanding that, and really in my experience, it's mainly just about recognizing when you are multiplying by 0. So if I have a really complicated multiplication like 627 times 4.75 to the third power, but it's in a group and multiplied by 0, I know the answer is going to be 0. I don't have to go through all of that calculation to figure it. But also, let's say I have 3 times some numbers in parentheses. But if I'm able to calculate and understand what makes 0, and that I have 8 positives and 8 negatives, that's going to be 0, then the whole thing is 0. So really, an understanding of the multiplicative property of 0 and being able to recognize 0 can make a lot of your higher mathematics go faster and without doing all of the work for it. Link number 5 for Zero My Hero is all about fractions and zeros. When there is a 0 in the numerator and when there is a 0 in the denominator. And really, it's understanding what the numerator and the denominator mean, and then you can understand which one actually exists and which one can't exist. So if you remember in a previous video on fractions, you know that the numerator is the number of pieces that you have in your fraction. The denominator is the size of those pieces. So if I have 0 size 1s, well, I have 0. If I have 0 size 2s, I have 0. And if I have 0 size 10s, I have 0. All 3 of those fractions are actually equivalent because you have 0 pieces out of this many that makes a whole. So if only 1 piece makes the whole, I have 0 pieces. If it takes 2 to make the whole and I have 0 of them, then I have 0. If it takes 10 pieces to make the whole and I have 0 pieces, then I have 0. Let's look at that when you have 0 in the denominator. If I have 1 piece but 0 to make the whole, how is that possible? If it takes 0 pieces to make the whole and I have 1, it doesn't make any sense. Same with if I have 3 pieces and it takes 0 to make whole, and 10 pieces and it takes 0 to make whole. Not to mention the number 0 being your whole, meaning your complete is nothing. So your complete is incomplete. Also, fractions are divisions. And so if I write this as a division, 1 divided by 0 equals what? So something like this. 1 divided by 0 equals what? Well, we can try and figure that out by flipping it around into a multiplication problem. So I simply reversed my division problem into a multiplication problem. And you can do that with anything. 1 divided into 0 groups. Huh? How can I not have a group if I have 1? I have to have at least 1 group. Well, when you switch it into a multiplication, it becomes what times 0 is 1. We just learned that anything times 0 is 0. It can't be 1. So this number here truly doesn't exist. It cannot be plotted on a number line because it doesn't exist. It's not real. It's not even imaginary. It doesn't exist. Okay, link number 6 of Zero My Hero is the 0 power. That means any number to the power of 0. And as you know, an exponent tells you how many times to multiply the base times itself. So if you're multiplying the base times itself, 0, how is it equal to 1? Because anything to the 0 power is 1. That's the, what's it called? It's another property of 0. The exponential property of 0? Something like that, but that doesn't sound right. Here's an example. So, if you have 3 to the 3rd power, that means 3 times 3 times 3, 3 threes. That's 27. 3 to the 3rd power is 27. 3 squared is 3 times 3, so you have 2 threes. That's 9. 3 to the 1st power is 3. There's only 1 3 there, which is equal to 3. Well, then how can we use this to figure out what 3 to the 0 power is? You have to look at the progression. How is it changing as you go from the 3rd power to the 2nd power to the 1st power, or even in reverse? If we look at the progression as it goes down, 27 divided by 3 is 9. 9 divided by 3 is 3. So the next one would be 3 divided by 3, which is 1. If you look at the increasing power progression, you're going to say, well, what times 3 would give me 3? What times 3 would give me 3? Because 3 times 3 is 9, and 9 times 3 is 27. Well, what times 3 gives me 3? It's 1. Any number to the 0 power is 1, including x. You can also look at that as the roots. So if I did the statement 3 squared equals 9, I'm going to write that as a square root statement. 3 is the square root of 9. So notice the square is the degree of your root also. Well, if my degree of my power is 0, then the degree of my root would have to be 0. Right? And 9 was the answer over here, and it was under the radical. So 1 is going to be under the radical. So any number to the 0 power is 1. And the 0 root of 1 is any number. Next are the links that connect to 1. 1 I call the master of disguise because you can represent 1 in a lot of different ways that I will describe to you. The first link for the number 1, and 1 is the master of disguise, is the fact that adding 1 is just like counting in sequence or counting on from a number. So any number plus 1 is the next number in the sequence. So 1 plus 1 is 2 because 2 comes after 1. 10 plus 1 is 11 because 11 comes after 10. 3,789 plus 1 is 3,790 because that's the next one in the sequence. It also works in reverse. Any number minus 1 is like counting backward. And that's something that a lot of kids struggle with, is counting backward. You need to do a whole lot more of that at the younger grades because it really helps teach subtraction. So 13 minus 1 is going to be the number that comes before 13, which is 12, etc., etc. This next idea of 1 is the master of disguise is the first disguise that 1 takes. And that's the understanding that a fractional 1 as the concept of whole means you have all of the pieces. So you have an integer written as a fraction, a rational number. For instance, 1 is one piece you have, and it takes 1 to make the whole. 1 out of 1 is 1. I can write it another way. If I have 2 pieces, and it takes 2 pieces to make the whole, then I have 1 whole set. I can do it again. 3 pieces out of 3 to make the whole. 1,255 pieces out of 1,255 pieces to make the whole. Or X number of pieces out of X number of pieces. What do you notice about all of those? It's the same numerator and denominator. Any fraction that is written with the same numerator and denominator is equal to 1. So you can actually write 1 in all of these different forms. You can disguise it, is what I called it, but this is the main idea for how you get fractions into common denominators. You're simply multiplying by 1. Here's an example. If I'm trying to add 1/2 plus 2/3, I'm going to use this form of the number 1 and this form of the number 1 to do that. So in order to keep this half the same size, I have to multiply by 1. That's the multiplicative identity. And when you do your multiplications, you have 3/6 plus 4/6. And the funny part is 3/6 is the same as 1/2. It's worth the same value. And 2/3 is the same as 4/6. It is worth the same value because that's truly what equal means, is same value. Equal does not mean identical. It means of the same value. And those 2 fractions are equal. And these 2 fractions are equal because I multiplied by 1. We already talked about the additive identity, and that if you add 0 to a number, you do not change that number. It does not affect the original number. It's an identity. There's also a multiplicative identity, and that multiplicative identity is multiplying by the number 1 in any form. So if I had 1 times a half, that's multiplicative identity because I still have half. If I do 4 times 1, I still have 4. If I have x times 1, I still have x. I haven't changed the original to my problem. If I do 8 times 2 over 2, that's still 8. It could be written as 16 over 2. Yeah, could be written as 16 over 2, but it's not, because 16 over 2 is the same thing as 8. They're all the same because I'm multiplying by 1. I haven't actually changed this amount at all. It's the multiplicative identity. And that also comes into play when you are solving equations that are of the multiplication type. So if you have an equation that has a coefficient, like this, 3 times a number equals 15. Well, I can get rid of the 3 by making it such that I'm actually multiplying the side by 1. Watch this. I divided this side by 3. 3 was multiplied by x. I divided this side by 3. And now you see the 3 over 3? That's 1. That's what I call the big 1 theory. Because that equals 1. And what is 1 times x? X. So essentially, I just made this side equal to x. But because it's an equal sign, if I divide this side by 3, I got to do the exact same thing or something of the exact same value to the other side. So I divide 15 by 3. And then simplify the sides, making x equal to 5. Multiplicative identity right there. Link number 4 to 1 is the Master of Disguise. It's all about powers of 1 or to the first power. Powers of 1 means that 1 is your base and you're raising it to a different exponent. So 1 to the third power is 1 times 1 times 1, which is 1. And it stands to reason that 1 to any power is 1, is itself. When you get into the negative exponents, then you're actually making it a fraction of 1 over 1. 1 over 1 times 1, 1 over 1 times 1 times 1. So it's just the flip, the reciprocal of the positive powers. All of them are equal to 1, including 1 to the 0 power. Because what's anything to the 0 power? 1. The other one is raised to the first power. This is where you have a base raised to an exponent of 1. So that means that the base is multiplied just once. So 3 to the first power is 3. And it stands to reason that any number raised to the first power is the base itself. So 4 to the first power is 4. 10 to the first power is 10. 8,275.9 to the first power is 8,279.9. Or however I said it. It would be the exact same number. There are many, many identities that you could go into that are all about 1 and powers of 1 and multiplying by 1, but this video is already getting really long. I perhaps should have divided it into a video about 0 and a video about 1, but I think you get the point. Our last link, and 1 is the Master of Disguise, is about fractions with 1 either in the denominator or in the numerator. So if you have a fraction with 1 in the denominator, then so like 3 over 1, or 3 wholes, you have 3 pieces, and it only takes 1 to make whole. So I have more than enough, because I have more pieces than are needed to make a whole. So I have extra. This fraction here is a special kind of fraction because you have a 1 in the numerator. It is called a unit fraction. Unit fractions are one of the ways you use, one of the techniques you use to count fractions when you're teaching adding of fractions. 1/3, 1/3, 1/3. So 1/3 plus 1/3 plus 1/3 is 3/3, which is whole. But a unit fraction has one piece of a certain size. So if I have one piece and it takes 3 to make the whole, then I have 2 more pieces I need to get. I have only 1 out of 3 that are needed. That's a unit fraction. Some of the common errors in understanding are not knowing all the ways to make 0 and 1. And there are some creative games you can do to understand that, and I'll get that in the next slide. But not knowing when these ideas apply and the value of the identity properties and when you're using them, and actually being able to recognize when something is an identity property. It's because there's a lot of times identities are taught completely out of context as if, oh, we don't really need this, this is just what we call it. But it actually comes into play with fractions, as I showed you, and with powers, and with solving equations. There's lots of ways that that identity is used. And when you understand it at the lower level math, when you get up into your Algebra 1 and Algebra 2 and Trig and Calculus, and you have all of those identities, you understand because you've seen them used before and you've heard that word before. These are some of the common errors in understanding these concepts and what they might lead to. Here are some activities you can use to reinforce these concepts. Number one, counting games. Things that go, what comes after this number? What comes after that number? What comes before this number? What comes before that number? When you're talking lower level, kindergarten, first grade math, even preschool. What number comes before? What number comes after? Those are good counting games. Also, songs. Counting songs that go up and counting songs that go down. Sometimes I think that people think that counting backwards is just understood and it's just easy, but I've worked with a lot of kids in tutoring that can't count backwards. And that's where their first sort of chain link breaks in their understanding is in subtraction. They don't know how to subtract because they don't understand counting backwards. So make sure your students know how to count backwards. There are puzzles you can do for creating 0 or 1. So one of them is you just take 4 dice, and they can be just regular 6-sided dice. You can use 10-sided dice. If you want to get really challenging, you can use the 20-sided dice. Roll 4 dice, and using any and all operations, see if you can make the numbers you get equal 1 or equal 0. So sometimes it might be possible, sometimes it might not be possible, sometimes it might be more challenging than other times. But getting kids to look at numbers and being able to manipulate them in their head using adding, subtracting, multiplying, dividing, exponents, parentheses, any kind of an operation to make it equal 1 gets them thinking about what these numbers can do, and they start practicing doing that sort of manipulation in their head. The big 1 theory is what I called my getting fractions to a common denominator, and then I ended up continuing using it throughout fractions and powers and equations. But it's basically the number 1 can be written in many different ways, and that multiplying by 1 allows you to change the form of a number without changing the amount. So if I multiply by 3 over 3, I can change the form of what I'm multiplying into a fraction, but I'm not changing the amount. It's the exact same size, exact same quantity. It's just in a different form. And you can do that with lots of different forms of 1. Practice balancing equations. So I used to draw a line where the equal sign is, and we would call that the brick wall. And we would do these over and over and over and over and over again. The more practice they get, the better they get at it. But I would make them write it out. The first several lessons we did, they had to write what they did on one side, write what they did on the other side, show the balancing. Once they got it practiced at least 60 times, then I would let them start doing it in their head, but not until then, because that reinforces the vision of seeing that they're doing the same thing on both sides of the equation. Also, just discussing why certain methods work. There are other methods of solving equations. Why do they work? And what you'll find is they are actually all doing the same thing. If you, I've seen one where you have, if you have one added on this side, then it's a subtraction on the other side. Well, how do you get to that? It's the same thing as the brick wall. If you add 1 on this side, you subtract 1 from both sides. That's how it becomes a -1 on the other side. These discussions and why it works helps them to understand and see the connections, which makes it easier to remember. But then the rote practice and writing out their work is what solidifies it in their mind and makes it much more memorable. Both things are true. You need the discussion and the concept understanding, yes, and you need the skills practice, being able to write it all out by hand. I would always make a bonus question on my tests and give them an equation or something that we've been working on, and I'd say, this is the answer, prove it. Or this is this, prove this one is not the answer. And they had to show me conclusive proof in order to get the points. We always practiced this skill, usually during a Fun Friday section when we would be working on stuff like that. So we had done it before. And the better they paid attention, the more bonus points they got. Thanks for watching this second edition of my Connections series videos. I hope you found it helpful, and I'll see you in class.